in the Americas, and good afternoon if you're joining us from Europe. We are here today to talk about the latest innovation in bulk storage technologies. Bulk storage is increasingly more and more important as more renewable energy integrates into the grid, and also as an important resource for grid management. So here with me today we've got 4 experts, and I'm going to start introducing them and asking them if they can please also tell me where they're joining us from. So first up would be Grant Grotox from Mac Group. Hi Grant, where are you joining us from today?
I'm joining from Madrid in Spain.
Excellent, thank you very much. Next up will be Oliver Schmidt from Imperial College London. Hi Oliver, where are you joining us from today?
Hi there, I'm joining you from Paris today.
Excellent, thank you very much. And we have also with us Eduard Heindl from Gravity Storage. Hi Eduard, can you say hi?
Hi, yes, I'm here in Germany, South Germany, Black Forest, actually.
Excellent, thank you very much Eduard. And last but not least, Robert Werner, also from Gravity Storage. Where are you joining us from today?
Well, I represent the northern part. I'm calling today from Hamburg.
Excellent. Thank you very much, Robert. So, as you can see, a lot of international crowd here, and we want to hear from you. Where are you joining us from? So, I'm not going to take any much more of your time, as it's important that our experts launch into their presentations. So, I'm just going to ask for that screen to go down so that, Grant, you can share your screen and you can begin your presentation. And whilst Grant gets his screen up, I just want to let you know that we're actually recording this session, and you're going to have access to both the session and the slides, and we will send this to you by email in a link, okay? And that if you want to ask any questions, there is a Q&A box at the bottom in your toolbar, and you can send that to us promptly. So thank you very much, Graham. I leave the stage to you.
Thank you, Belen. Firstly, I would like to say hello to all of the participants in this global webinar on the latest innovation in bulk storage technologies. My presentation will focus on the key drivers that are propelling a growing demand for bulk storage solutions to provide utility and network scale integration of renewable energy. My aim is to provide the context for the presentations that will follow on the levelized cost of storage for alternative bulk storage technologies, and then the presentation of the innovative gravity storage solution that has been developed by Heindl Energy. The first question to address is, where is the global renewable energy market heading? And what are the consequences in terms of balancing demand and supply of energy from solar and wind resources that are inherently intermittent sources of power? As my first slide shows, over the years to come, there will be an inexorable rise in the market share of solar and wind power within the global energy mix, bringing with it the challenge of integrating such high volumes of intermittent power into existing electricity grid networks. Storage is and will be ever more critical to ensuring that the growth of solar and wind can reach its full potential without being constrained by the limitations of regional, national, and international grids. The global storage market is forecast to grow at an exponential rate over the coming years, reaching annual deployment of over 20 gigawatts of storage solutions a year by the middle of the next decade. As the graph shows, the integration of utility-scale solar and wind projects will account for a large part of this growth, as will grid ancillary services and load shifting of renewable energy generation to balance electricity demand and supply. Bulk storage refers to that segment of the storage market that responds to grid-level balancing needs, with storage solutions of hundreds of megawatts to several gigawatts of hours of storage, with discharge times of several hours per discharge. Today, the only fully mature bulk storage technology that can meet this need is pumped hydro storage. And the strength of demand for bulk storage solutions is clearly shown in that, in addition to the 170 gigawatts of installed pumped hydro storage plants today, there are over 100 new PHS projects in planning or under construction globally. And that represents an additional 75 gigawatts of new bulk storage capacity. However, pumped hydro storage faces significant deployment challenges due to topographical and hydrological constraints, as we shall see later. Therefore, there's been an increasing focus on more flexible alternative technologies, such as compressed air energy storage, liquefied air energy storage, and gravity-based solutions. To date, the commercial deployment of these new technologies has been very limited, but the need for more flexible and cost-competitive bulk storage solutions remains, providing a fertile ground for innovative technologies. In addition to the ubiquitous increase in renewable energy generation, there is a further phenomenon that is fueling the need for bulk storage solutions globally, and that is the rise of the mega or multi-gigawatt solar and wind project. Over the past years, there's been a clear trend to the build-out of solar plants and wind farms of many hundreds of megawatts in capacity, as well as the planning and start of construction of multi-gigawatt solar and wind projects and hubs. We are now regularly seeing the records for capacity installed at a given site being beaten. For example, the planned 10 gigawatt solar PV site being developed by Adani in Rajasthan in India. We are also seeing the planning and commercialization of nodes of solar and wind energy that are focused on a national or often interregional market with high capacity, high efficiency transmission networks, allowing the flow of green energy between supply and demand across regions and grids. The example of the Asian Renewable Energy Hub, with a combined 6 gigawatts of solar and wind power generation, aptly shows the scale of future renewable energy production and the consequent commercial attractiveness of gigawatt scale storage solutions. In my last slide, one can see that pumped hydro storage solutions are already being deployed to support ambitious growth of gigawatt scale solar and wind generation, such as the Al Hatawi pumped hydro storage project that will support the grid integration of the planned 5 gigawatts of solar power from the Rashid Al Maktoum Solar Park in the United Arab Emirates. However, pumped hydro storage has many limitations in terms of the sites where this technology can feasibly be deployed. This is due to the very unique topographical and hydrological conditions that limit the degrees of freedom for the deployment of pumped hydro storage. There are and will be many, many locations where only more flexible bulk storage solutions can feasibly be deployed. It is here that new, flexible, and cost-competitive bulk storage solutions will find their market. Let me now hand on to my fellow speaker, Oliver, who will discuss the cost competitiveness of alternative bulk storage solutions with some very interesting conclusions. Thank you.
Thank you very much, Grant. If you can just, excellent. Oliver, whenever you're ready. And just a reminder that you can ask any questions through the Q&A box. And go ahead, Oliver.
Yes, can everyone hear me now? I think it should work, yeah.
Yes, we can hear you perfectly.
Thank you, Belen. Thank you very much. I would like to talk about how to assess the cost of electricity storage technologies and then apply this to bulk storage technologies. What I will present is the result of my research at the Grantham Institute at Imperial College and a project I conducted together with Heindl Energy. So currently, I feel analyst studies and industry reports focus very much on the investment cost of storage technologies. A prime example of this is this chart, which you can see on the slide, coming from a Nature Energy paper. On this chart, you can see the historic reduction in product price for different storage technologies as a function of global deployment. And while such an analysis can be very powerful if you, for example, want to predict the future investment cost of storage technologies simply by projecting these historic trends forwards, it's not sufficient in order to look at how expensive a storage technology is in a particular application and how the technologies compare to each other. And that's because of three reasons. First of all, rarely these investment costs are application specific. They might change whether you want to use one and the same technology for bulk storage or for frequency response. Also, investment costs are not always referring to a fully installed operational system, but sometimes to the cost of battery packs or cells only. And most importantly, we only consider investment cost and not operational cost or replacement cost. And also, we do not consider crucial performance parameters like the round-trip efficiency of a storage technology or the usable storage capacity. And that's why an appropriate cost assessment of storage always has to be application-specific, refer to the entire system, and consider all cost and performance parameters that are relevant throughout the storage lifetime. And this is where levelized cost of storage come into play. This metric quantifies the discounted cost of the discharged electricity. Or in other words, it tells you how much does a unit of electricity discharged from your storage device cost. On this slide, you can see a simplified formula for levelized cost of storage, considering the investment cost, operating cost, and disposal cost, divided by the electricity discharged over the entire lifetime of the storage technology. In that sense, levelized cost of storage is comparable to levelized cost of electricity for power generation technologies. And when we look at the input parameters in this formula, they might seem familiar. However, when you look at the denominator, the electricity discharged throughout the entire lifetime of the storage technologies, you can see the complexity of levelized cost of storage analysis, because here we consider unique storage parameters like the round-trip efficiency, the depth of discharge, the limited number of cycles, and the degradation throughout the lifetime of the technology. And by considering all of these factors, levelized cost of storage are an appropriate tool to compare storage technologies. Although there has been some great work on LCoS by the consultancy Apricum or by Lazard's levelized cost of storage analysis, it's still a relatively new metric. And I would just like to highlight a few points you should be aware of. So in this slide, you can see the different cost components of levelized cost of storage. And these are things to be aware of. I'm going to highlight the ones that are maybe not obvious. The first one are replacement costs, which sometimes tend to be forgotten or are sometimes included as an annual share in the operation and maintenance cost, which is not the right approach to take. The next thing to highlight are charging costs. In some levelized cost of storage analysis, these are excluded based on the argument that the power price is not intrinsic to storage technologies. People who do that then differentiate between levelized cost of storage, excluding the charging cost, and levelized cost of discharged electricity, including these costs. However, when you do that, you also neglect the round-trip efficiency of the storage technologies. And that's why common practice now is to include this and to call it levelized cost of storage. The last thing I want to highlight is the other cost component, which I didn't include on the previous slide. These can be taxes, for example, and they only apply if you have a very location-specific project in mind already, where taxes would matter. If you only want to compare different technologies, you can exclude this cost factor. So I think now we're ready to perform a levelized cost of storage analysis ourselves for bulk storage application. On this slide, you can see the input parameters that we are using. These are the substance of any levelized cost of storage analysis. You can see the application parameters that are given by our application, bulk storage, and you can see the technology data that we're using. I would like to highlight that the first 4 technologies you can see are the most widely deployed storage technologies on the planet, which is why we chose them. And they're also used for bulk storage. in particular the first two. The data we're using for them come from, in my view, credible literature sources that build on manufacturer quotes and actual project data. The fifth storage technology is gravity storage, and the cost and parameters you can see here are the ones anticipated by Heindl Energy. So I would really like to highlight, my light just turned off. I would like to highlight that you should really take a critical look at these input parameters because, as I said, they're the substance of any levelized cost of storage analysis. Now let's take a look at the results. On this slide, you can see the levelized cost of storage on the y-axis in dollars per megawatt hour discharged electricity. And on the x-axis, you can see the different storage technologies. It appears that gravity storage comes out as the most cost-effective storage technology in bulk storage application. This is because of the relatively low costs that are associated with the components that store the electricity and the moderate cost of the components that charge and discharge the electricity. So the costs are around $148 per megawatt hour. The next cost-effective technologies are pumped hydro and compressed air at around $200 per megawatt hour. These technologies benefit from very low costs associated with the components that store the energy, but these technologies also have relatively high costs associated with the components that charge and discharge the electricity. Lithium ion and sodium sulfur come out at above $300 and $500 per megawatt hour for bulk storage application. You can see that for all storage technologies, the investment cost component, here called CapEx, is the most significant cost driver. The charging costs, or P-elect, are the second most significant cost driver. And finally, I would like to highlight the error bars. These represent the levelized cost of storage results of Lazard's study in 2016 for the same technologies in a similar application. And we use these in order to qualify our results. So for pumped hydro, we are at the higher end of this range because the investment costs that we assume are at the higher end of what Lazard assumes. Our results for compressed air are much higher because we do include replacement costs that are excluded from Lazard's study, and we use the efficiency of that technology of 40%, which is more realistic for conventional compressed air than the 70% used in Lazard's study. For lithium ion, we're at the higher end of the range because we consider the degradation of the technology, which is not considered in Lazard's study. And although the same is true for sodium sulfur, here we are at the lower end because the investment costs that we assume are below the ones assumed by Lazard. So I think this is a prime example of how the methodology, by for example including degradation, and how the input data are really the substance of any levelized cost of storage analysis and can significantly impact the results. Finally, I would look at the sensitivity of our results as a result of the discount rate and the project duration. So we can see that a discount rate of 4% compared to 8% has a significant impact on reducing the levelized cost of storage for all 5 technologies. Since a lower discount rate reduces the discounting of all the electricity discharged over the entire lifetime of the technology, those technologies with a long construction time and operational lifetime benefit the most. Gravity storage with a discount rate of 4% could be pushed below $100 per megawatt hour. And lastly, project duration. If you were only to look at a storage project that you want to operate for 11 years, which in this case would be the construction time and the operation time of lithium-ion batteries, the levelized cost of storage for lithium-ion wouldn't change. However, for all other technologies, they would significantly increase because you're basically disregarding all the electricity that could be discharged over the operational life of the technologies. And this again affects those technologies with lifetimes of up to 60 years the most. And this is the end of my contribution. I'm looking forward to all the questions you have. I also invite you to look at the website of Storage Lab, which is an independent research hub led by me, to see all the findings that we have about electricity storage technologies. Thank you.
Thank you very much, Oliver. So now that we've heard everything about the study that you did, and we're going to hear about the innovation. So Eduard, I think you're next up, and you're going to tell us a little bit about your idea and your work. So remember to unmute your mic and then to share your screen. And in the meanwhile, whilst Eduard gets set up, I'd just like to take the opportunity to remind you about the Q&A box and to make sure that that you remember that we are recording the session and that we will send you also the materials. Eduard, excellent. Can you just unmute your microphone so that we can hear you?
Yeah.
Perfect. Okay, so go ahead.
So, hello. Yes, I want to give you some introduction to the technical side of this graphite storage. First of all, our vision is that on the long term, we will have a complete renewable world using solar, wind, and other sources. And we need that for 24 hours. And that means we have to do that in a long and sustainable way. That means that the storage system has to stay as long as the different parts like the PV and the windmills. Now, how do we do that? The first thing is, let's look into the cycle of this storage for 24 hours. Oops, sorry, that was not, should start now. Yeah. What happens during daytime, we have solar and the energy is going into our pumps and pressuring water below the piston. This piston lifts and stores the energy in gravity. Now in nighttime, the pressurized water is going through the turbines, generating electricity and is supplying it to the grid, that we have electricity during 24 hours. So this concept, look a little bit deeper in there. The really interesting part is the piston. That is natural rock that was already there and that is excavated by us at this place. So we don't have to move too much part, and the piston itself is stabilized where necessary. Below the piston is the pressurized water. We are working with a pressure about 70 bar. That means that the pressure is very similar to pumped hydro. That gives us the advantage that we can use well-known pumped hydro technology, including the well-known efficiency of the systems. We also need a water pond to have the water available, and we bring the water between the pond and the lower part of the piston. That means we have to fill it once, and then it works forever with more or less the same water. So we don't have a water problem in a desert, for example. The size matters here very much. If we have 250 meters, we have 8 gigawatt hours of storage, and it is 340 meter deep. That's quite little bit deep. So we have to understand how we build that system. And here we have a short animation. After clearing the site, we start at the center where the piston is coming, and we drill down shafts for the equipment. And then in parallel, we meet down there, and then we cut the lower part of the piston. Then we bring building for the turbines. And the last big step is introducing the sealing ring. That is a very interesting part. And of course, the water pipes for high and low pressure. This system now in some more detail. The excavation of the annulus needs an equipment that can cut hard rock. There are 3 ways today available. It's drill and blast. We don't prefer that because that may destroy our piston or weaken it. We can use cutting machine as well known in the mining industry, or we can use wire saw, a new and very efficient way to cut rocks. Then the cutting machine is going down deeper and deeper, all the 340 meters. The other thing we have to do is we have to make the surface of the rock waterproof. We don't interfere with the environment, and we don't want that water is spilled out in the high pressure part. So we use therefore concrete and steel, and this is the material of choice because it can give us the easy production of that. So after that is done, we look into an annulus that is 340 meters deep, and we have now a piston with 125 meters and an open width here of 4 meters. How to make that work for the button? That is the separation of the piston base. Here we use a central tunnel and some smaller tunnels for work, and some concrete processing and a so-called cutting machine, well known from mining. And now we have to cut these pillars here, and we look into the detail how this is operated. We cut through the rock, and we don't want that the rock is open hanging here. So immediately after that, we introduce 2 shields of metal and concrete at the lower and upper side, resulting in very stable pillars. So the ceiling and the material of the ceiling is more or less the same as you see on a conveyor belt. And now move up, and you see the seal is running here along. And the advantage of this technology is that we have a self-centering system. We can control the high pressure because all this material is well known. Where can we build something like that? The point is that we need solid and rock without too much faults. That is available in many places. We did a global study together with DMT about 120 sites where boreholes were available, and we have seen that half about the sites have suitable rock, and there are some rocks really excellent for our technology. So we usually would start at the best places, and then I think we have enough places. To give you an impression how large the system is, here we have a big solar farm, and we see the small, comparably small gravity storage. And this storage is enough to store the whole day of solar energy of this site. That's a site with 1 mile by 1 mile and 120 megawatts. Come to the conclusion. What do we have with our system? We have the applicability that we don't need the elevations as we have learned from pumped hydro. That is a very efficient way. We have more than 40% of the Earth surface that can be used, so we'll always find a place where to do it. We have very high efficiency. That was interesting for the levelized cost of energy, as we have learned. And we can use the system for many other services in the grid. For example, black start, rotating masses are very convenient. Our discharging time can exactly be tailored to the operators. So we are not dependent on the amount of rock. We can use as much turbines as we think is the best solution for a special application. And the last I want to go in detail is sustainability. We have minimal raw material, just rock and water. And even if we dispose the system at the end of lifetime, there is only rock and water. That is not a big problem. And so we have also a small land footprint, and we have a small use of water. So that's it for my part. Thank you for your attention.
Thank you very much, Eduard. And there has been already a few questions about, whether this is being done or is being done anywhere. So I think that this is exactly Robert's cue. So you can just show us your screen, please, Robert.
Yes.
And I have to say, guys, you are doing great for time. You're doing a great job. So thank you very much. You can just put that in. And as you know, just a reminder, I know many people, if anyone has joined us, we are recording this. Presentations will be made available. Send your questions through the Q&A box. Thank you very much, Robert. Go ahead.
Okay, thanks a lot. Hello, everyone. I would like to add some information about the status of our development. And then finally, I would like to be more detailed on the economics of this system. And I want to invite you and trigger a discussion about how economically are bulk storage and what role can they play in the future supply. Well, here you see a graph about our planned path for the size development. As Eduard mentioned, it is important to understand that this system only will be economically feasible if you have a certain size of the diameter. So we have to develop this technology in several steps. And we did a lot of research in the last 4 and 5 years with a lot of theoretical studies and scoping studies, etc. And now is the time we want to transfer this into a proof of concept. That means we want to build a small edition of this system, 20 by 30 meters, and it will have no impact on a certain business case in the grid or so. It is just about to test the system and the ceiling. And after this is completed, hopefully by 2019, we want to have a first pilot project, which will be actually connected to the grid of, let's say, about 200 or even 300 megawatt hours capacity. But still, we want to go for more and plan to have a first commercial size with 150 meters. And this is the size you actually need at least to be economically fair in a regular grid or in the market design. We know it so far. And as larger you will be, as cheaper will be the price for storage capacity. Well, on the left side, you see, just to mention it, a few partners. We work since years together. So we are a team of coordinators of several development and researches. And we have a very close cooperation with Al Uni, a construction and contracting company from Saudi Arabia. They have a lot of queries, and they offered us and invited us to use them to build such a demonstrator. And maybe some of you know that we have a very nice geology, good granite in Saudi Arabia. And it is a country where we have a lot of development referring to renewables. And we have the techniques and all the companies there to build this. So thanks for this invitation. And this proof of concept is to prove the technology, especially those parts which are very new. And this is mainly the ceiling, because all the other components are quite well known, either from mining, tunneling, or from pumped hydro. But the ceiling, as Eduard showed, that's tricky, and that's something we have to test, and we will test it in real scale, one by one, as we will use it in the commercial size later on. We also create pressures beyond 70 bar with a special construction, so we can invite everybody to test themselves, to make measurements, to do research, etc. The plan is that we can start with operation of this testing site in 2019. And this is just a little piece of the plannings which are on the way right now. You see the geological survey, the results is marked in here with the red lines. These are fractions, and it shows you that we are not afraid of fractions, but we have to look at it, how they are, how deep they are, and how we can manage them. And of course, you have this tunnel, and here you have the piston, which will be lifted up later on. This is a view from the top, and here you see actually the site. where we want to build it. And from the top, you see that there's the water reservoir in the blue, and here's the terrestrial survey. And so that's the way how we do the assessment of sites when we do this project. Okay, let's talk about money. The revenue models for gravity storage are the same as we know it from bulk storage, but I think we have to discuss what are the revenue streams for bulk storage in future. And well, you probably know that we have three basic models, like a traditional arbitrage model or PPA, you can use it. You produce during the day with wind or solar, and you take part of it to transfer it to the night. And the big vision behind bulk storage and renewable is that we will sometime we want to be able to deliver 24/7 with renewables. And this is something which is highly attractive in terms of economics. And that's why we definitely will need a bulk storage to cover these huge amounts of electricity. But you know that a lot of grid operators, they really are worried about the stability of the grid. And we analyzed what is the reason why at present so many pumped hydro storages are in planning. And the reason is that they need capacity to balance the grid, to provide balancing power, to do voltage support, etc. And this is very important, and it's getting more important. That is to prevent blackouts. And as you know, that it takes one or two blackouts, and the damage of the blackouts are far more than the whole storage would cost. So this is a thinking we see a lot in market models, and as you have probably heard that even the EU now wants to allow storage to be run and operated by grid operators, which was just 2 years ago it was a complete no-go, and you see how things are changing towards storage. Now, just last slide on the figures concerning gravity storage. We did a cost study and developed a financial model. So the condition is 8 gigawatt hours capacity, excuse me, and the costs for charging power is at 3 cents US cent per kilowatt hour. These are the very important inputs and assumptions. You come up with capex of 1.7 billion US dollar, calculated in euro at a German cost level, 2016. Of course, these capex will vary depending on what region you will build it. The OPEX, and this is interesting, they are below 1% as far as we can calculate this per annual. And it includes mainly the costs for maintenance of the ceiling, and even once in a while you have to change the ceiling material, which will be possible perfectly. So the revenue, of course, it depends on how many cycles you will run and what is the output for the price for the discharged energy. And we assume 330 cycles a year. The rest of the days you have maintenance, and we assume that you sell it for $100 US per megawatt hour, which is quite fair. We know that a lot of pumped hydro storages, the new ones, they have to sell at far higher prices. The IRR, and I think that's the big message, is always double digit, and it is without any subsidies. you know that about 100% of all pumped hydro stations are subsidized in CapEx for good reason, because it's purpose to ensure security of supply. So this is calculated without any subsidies, but that means that the payback time might be a little bit too long for many investors, 16 years, but please consider it's a lifetime of at least 60 years. And I think this is a very good perspective for bulk storage and for the renewables as such. Well, I think I've seen there are a lot of questions, and I want to finish now, and would like to invite you, if you're interested, to join this technology, to learn more about, or to even engage yourself in this technology. Please contact us. We'll be happy to hear from you. Thank you.
Thank you very much, Robert, and all of the panelists. And yes, I also would like to encourage you, if anyone is interested in being in touch or getting put in touch with Robert and with Eduard, you can send us an email and we're happy to do that for you. We have indeed a lot of questions. So I'm going to start, if you don't mind, with one on my own. I know this may be basic for some people that are listening and even for yourselves, but I think it's important if anyone can ask or answer succinctly, what is the difference between bulk storage and large-scale storage? Because I think there is a little bit of, there may be confusion in that. So I don't know who wants to take it. Robert, you want to take it? You're looking really like propped up for it. Just make sure you mute. There you go.
Okay, I think there is not a real difference. The point is, large scale is usually everything beyond batteries or everything beyond hundreds of megawatts. And so then you store a lot of stuff, and that's bulk. But so I think there is not a technical difference. It's just the same. It's different wording.
Okay, thank you very much. And now I've got a question that came actually in the chat that said, the Californian market may be one of the earliest for bulk storage. Do you have a site for gravity storage there, or proof of concept? And I'd like to widen this out. You know, they mentioned California. Are you guys planning anything in California? And also widen it out, and what other places, countries are good for this type of technology?
Yes, thanks for this question. It's matches perfectly, because we'll start for a trip to California next week. So you can meet us on February 13th in San Francisco on a conference, in a type of symposium. But of course, the target markets are those areas and regions on the globe where we see a fast growth of renewables, and where we have a fairly good geology to build this. And this is, of course, the US. This is the Middle East, where we see a huge deployment of PV. This is China. This is India. Of course, Australia. And but we think it is also very suitable for Europe to capture the offshore wind. But the message is that in all countries and nations, we see a certain area where we can build it by geological means. And this is the big message.
There was another question here that said, have you considered using steep hillsides, a version of your project in steep hillsides to reduce construction costs?
Yeah, thank you for this question. It is an interesting point. As you have seen in our first demonstrator, we will also use a hillside, because then we only need a tunnel. It shouldn't be too steep, because within the system we have high pressure, and so we need some rock mass around. But a hill is quite a preferable situation, as long as it is not too steep.
Thank you very much. Okay, a question for Oliver. Is the replacement cost not included in the O&M because it is paid as an insurance before the implementation of the storage system?
Yeah, I think that's a very good point, and that's also maybe the explanation why sometimes it is included in the operation and maintenance cost. However, I feel when you do that in a levelized cost of storage analysis, you're leaving the purely technical perspective, because then you also need to think about what is actually the insurance interest rate that I need to pay on that. And what we found in many levelized cost of storage studies is that people didn't think about insurance. They simply divided the replacement costs into annual shares and included these in operating and maintenance costs. And that's definitely not the way to go.
Okay, and also here a question about concentrated solar power. Will the molten salt two-tank technology hasn't been included in your? It's actually for Oliver as well. Will be molten salt with two-tank technology included in your analysis? They can easily store up to 1,000 megawatt-hour. So, is it cheaper potentially than the technologies that you have shown?
Yeah, I think yeah, this question sounds familiar, and I think Eduard or Robert are better suited to answer it. Just a pointer that I took away from previous discussions is that gravity storage is quite different to CSP because it stores electricity, and electricity in itself can come from multiple sources and is different to storing heat. So I think that is one reason why we didn't include it, but I hope that Robert or Eduard will also say something about this. So
which of you would like to take that question? Robert, Eduard? Remember to unmute your microphone, Eduard, so that we can hear you.
Yeah. Okay, as Oliver already mentioned, the point is our system is storing electricity from the grid. Of course, it is useful if there's a lot of solar energy, wind energy, or even other sources that don't match exactly what the demand is, because we have always the problem in the grid. There is the demand side and the production side. They never match exactly. We always need to balance that. That is done by our system. If you look into CSP, it is useful for the way that you can store, in this special case of concentrated solar, the energy beyond the time when the sun is shining. But the system is fixed to this type of generating heat. And that means you need direct sun. That is not so often available as indirect sun in a global scale. And so we think it is a different technology. It makes sense in some cases, but we think the gravity storage has the advantage that you directly can support the grid with all the different features we already mentioned. Berliner.
I'm sorry, I did it myself. Look at that. So, Eduard, question for you again. You mentioned you don't need elevation. Could you clarify how high the rocks would be elevated when the system is fully charged?
So, of course, depending on the size of our system, but if we have a full-size system with the 8 gigawatt hours I presented with a 340 meter deep, this system is lifted maximum 100 meter, not the full height. Reasons are because the pressure area should be small and the stability of the surrounding rock should not be challenged.
And what kind of materials are foreseen for the sealing around the rocky piston? You had this question before.
Yeah, it's a big point to seal the rock. We have also workshops on this topic, of course. Sealing the rolling membrane seal is one thing, and the other thing is the surfaces. What we suggest is that we have a thin steel layer of about 3-4 millimeters that is installed all over in the area where we have a high pressure. And so, because there is a well understood performance of the steel in pumped hydro systems, because they also have sometimes tunnels and stuff like that, where they have the same pressure and the same questions, and they usually take steel directly on the wall or in some other ways. So it is the first choice, but we are still looking in optimization, and we have seen new materials coming up from the industry that really can seal granite in an incredibly good and cheap way. So maybe in the future we can build it even cheaper as we think at the moment.
All right, so I'm just going to keep going because there are so many specific questions for you. So the gravity storage concept requires the rock to be fully impervious. Otherwise, the pressurized water below the piston will leak into the rock cracks, and that will cause the system will just pump water continuously into the rock. How do you manage this imperviousness issue?
So that is an interesting question. Yes, it is definitely not a good idea to have pressurized water in a rock. You may no fraction happens. And so, as I already told, we will cover the area with the high pressure, that is the lowest part of the rock of a piston, with steel. And behind the steel, we have also a control system that can detect if water is going for any reason through this metal shield, so that we can control that. And especially if we start building up the pressure, we can exactly measure if there's something not okay, but hopefully we can control that. And it is not unknown in tunnel construction and in construction of pumped hydros to control that situation.
Okay, and I suppose this is a question for everyone, and possibly Oliver. Are you assuming a fixed revenue from a government authority when you crunch your numbers, or are you simply considering energy pricing arbitrage, so like spot market? Who wants to answer that?
I'll take it.
Okay, go on, Robert.
Yeah, see, we have to analyze the market design in this region where this gravity storage will be built. You know, and I mentioned that markets work differently, and if we apply gravity storage or bulk storage in general for grid stabilization and balancing power in the grid and so on, of course, this will be in the business case of grid operators. And there's no market, you know, it's a natural monopoly. So it's a different business case as when we have an arbitrage model or a PPA where we have a production and storage together, and we have one price we can offer to the customers at day and night, and we mix it. But we calculate, our calculations are completely without any subsidies. So this is that's the best way. As soon as we start to integrate subsidies, we have to make an assumption about a certain market design. And these are studies we actually can do anytime. If there's interest, we can sit together and look, how is it working in the US? How is it working in China, where the subsidies are very high, for example? How is it working in the Middle East, and so on?
Okay, so given the large mass that is ultimately the generator of energy in your system, is there a limitation of the system to quickly respond to grid demands? Or is that not part of your expected use case?
Yeah, we expect, that's a good question. You see, the development of turbines and the steep speed up of the turbines, it really increased in the last years. And we talked, we had lots of talks to turbine manufacturers and pump manufacturers, and they all work on a fast reaction time. And as you know, a lot of pumped hydro stations are now being revised, and they changed the turbines to be on the grid within seconds. So we will be not as fast as batteries, and I think this is a real good, a good job relation between batteries and bulk storage. But the future bulk storage systems will be very fast on the grid.
Okay, so I'm going to do just two more questions because we need to cut it for today, I'm afraid. We have a lot more, but I'm just going to limit it to two. So one of them is actually a question that has come several times in different ways, but it's around the same thing. And it's all about the sort of the minimal economical size of gravity storage, okay? Someone here says 8 gigawatts is quite a big project. Someone else mentions is not really complementary to a power generation plan. Have you considered the scale modifications? So that would be the answer, really. What is the minimum viable project for this type of technology?
We expect that you need a size of about 120 meters as a diameter to be in an economic feasible range. It depends on the local market and the market design, but this is not a solution for small scale or for the garden in the backyard. This is not working. You should see that the average size of PV plants and also of wind parks is increasing dramatically. We see projects of 4 gigawatt in China, of 2 gigawatt in Australia, in Saudi Arabia, and in the US. And these huge plants, just imagine if you connect 2 gigawatt to the grid, it's a big challenge. And that's why I think you need this big storage solutions to levelize this and to balance all this and to stabilize the system. So our system really works on the large scale. And this is because, like Eduard told, if you enlarge the diameter, you increase the storage capacity by the 4th power. This is by physical means, but the construction costs will only increase by square. And that makes it so efficient, and that's why we advise to plan with 150 meters as a diameter.
And just the last question, before we leave, is like how many cycles, for gravity storage? How was this parameter established? I know that Robert, you probably want to answer this one.
Yeah, we calculate with 330 cycles a year. If you use it in a PPA model, this seems to be realistic. So you have about 10% of the time for maintenance, which I think can be reduced once you have the experience with this technology. Now, this is about what we calculate.
Excellent. Well, thank you very much. Thank you very much, Grant and Oliver and Edward and Robert, for your time. Thank you very much, all of the participants. I encourage you to reach out to either us ourselves or the people at Gravity Storage, or to Grant and Oliver if you have any further questions. I'm sorry we couldn't take them all. And without further ado, I look forward to seeing you again in the next time. Thank you very much. Thank you. Bye.